Very good morning to to all the people who are joining us today. Today Professor Gunes Karabulut Kurt is going to present a webinar on this advanced mobility webinar on the topic of mega constellations, satellite constellations. And Professor Gunes is a distinguished lecturer of Vehicular Technology Society, and she is also involved in the Committee on Space, Air, Ground, Water Integrated Communication Systems. She received several awards, and some of these awards include Marie Curie Fellowship, and she also received the Turkish Academy of Sciences Outstanding Young Scientist. And thank you, Professor Gunes, for accepting the invitation to give us this presentation. Please proceed.
Thanks, Kamesh, for this kind invitation. It's my pleasure to give this talk on advanced air mobility webinar series. So I would like to acknowledge the IEEE Vehicular Technology Society for their sponsorship for this series as a start. So my name is Gunes Karabulut Kurt. I'm a professor at the Department of Electrical Engineering of Polytechnique Montréal. And today my talk is on communications and networking in LEO Mega-Constellations. So it includes a lot on the air mobility concepts. I have been working on this topic very intensively since 2020, and currently I am the Canada Research Chair on space communication systems. So I want to start with a quick overview of my university here, Polytechnique Montréal. This is a 7-department engineering university that is affiliated with University of Montreal. We have about 10,000 students, and it's a research-intensive university. It is located on Montreal, at the top of Montreal, actually at the center of Montreal. So if you are planning to come to ICC, please contact me, and maybe I can give you a tour of the university. So today in my talk, I have divided into 6 different sections. First of all, I'll try to explain what is going on in terms of the satellite communications and satellite networking. As you are every 20 years or so, satellites are becoming very hot topic, both in research and industry. I strongly believe that this time it is very different, and I would like to explain the reasons how it will be different. So I'll start with this emerging mega constellation paradigm by giving the definitions. Then I will continue with the key game changers that is expected to change the paradigm of the industry, which is through the standardization aspects. Then I will go deeper in the technical concepts. I see mainly 2 difficulties in mega constellations. One of them is the point-to-point communications, and the second one is the networking paradigm. So I will delve into those. There are a number of future research directions that needs particular attention from the research community. So I will try to summarize those if you are searching for a topic on this interesting subject. And finally, I will conclude my talk. So regarding a definition of a satellite, when we are talking about satellites, it's usually natural objects. For example, moon is Earth's satellite. But when we are talking about satellites within the communication context, we are almost always talking about a human-made object that is launched into space. So these satellites actually are used for very many applications, not only for communication. Their use for communication is very much apparent with the emerging constellations. However, we use satellites in our daily lives by when trying to find the route that we are planning to pursue. We are using satellites when we look at weather forecasts. We are using satellites for space explorations, and also the satellites are very frequently used for military applications. So satellites in as a whole, they are not a single function entity, but multifunctional entities. But each satellite and constellation is specialized with its particular focus. So a classical classification of satellites lets us to divide them into 4 clusters, which include low Earth orbit satellites, LEO satellites, with altitudes frequently from 450 kilometers to 1500 kilometers, but they can go as low as 300 kilometers. Medium Earth orbit satellites, about 7 to 25,000 kilometers. Geosynchronous or geostationary Earth orbit satellites, they are around 36,000 kilometers altitude, and they rotate within the same speed of the Earth. And then we have to be able to cover, specifically to be able to cover the polar regions, we have high elliptical orbit satellites. So these are the conventional satellite classifications. An emerging new class is being taught after these days, very low Earth orbit satellites, maybe going down to 200 kilometers altitude. So the number of satellites is and also I'll show this later in a figure. The number of objects that we are launching in space is increasing at an exponential rate. And this is due to a transformation in the satellite industry. There is a significant momentum behind satellite communications and networking paradigm these days. And we keep hearing about ambitious mega-constellation plans of tens of thousands of satellites. And this generates a rejuvenated interest in this topic. So satellite communications has been around for decades these days. But the main difference is we see these satellites function in a more intelligent manner. They can do networking among themselves. They can help one another. And this is the main difference that we see from the classical bandpipe architectures. The main reason for these developments are the advanced payload architectures, better active antenna systems with more directional antennas and faster sweeping speeds, improved microwave, digital and optical technologies, better efficiencies of solar panels and batteries, and finally improvement in the ground segment technologies. So with these enablers, we can actually think of high data rate satellite networks. So the main difference between these ones and the legacy systems is basically enabled by inter-satellite links. So with inter-satellite links, currently we are talking about mostly laser inter-satellite links, but RF options are also being researched. They help us offload some of the networking functionalities to this to the space components. So we can use these satellites as networking elements. This lets us do better resource allocation and lets us to do better traffic management, enabling autonomous, intelligent, resilient, self-organizing and self-controlling capabilities. So as we cannot send technicians to the space to be able to tune the satellite, it's important that they have these additional functionalities. And this is the main driver of the transformation in satellite industry, of course, along with reduced launch costs. So when we are talking about satellite networks, actually, a very high number of components are being thought after. So tens of these plans, these numbers change almost in a daily basis. But it is clear that we will be seeing tens of tens of thousands of satellites in the near future, and they will have advanced networking capabilities. In addition to that, they will have advanced additional capabilities, like there are plans of um, uh, installing data centers through satellite constellations. So this is it is getting very promising from that perspective. It's very important because these satellites can help us provide ubiquitous global coverage. And that please take that with an asterisk, because it's details needs to be sought after. So these satellite, it's very exciting times for global connectivity through these satellites. If you when you read any kind of 6G paper that also talks about SAGI networks, integrated satellite, air, ground, and sometimes marine networks, uh, they all come with the promise of global internet access. And it is very important to be able to provide this global internet access is very critical because it is one of the key enablers to be able to achieve the sustainable development goals that are defined by the United Nations to make sure that all humanity um, uh, um, prospers in an equitable manner. So it's very important because when we are talking about satellite coverages, we are talking about very high footprint, large footprints, and they can provide significant coverage. What is different than today's networks? It's basically, I have this Canadian map. As you can see, of course, here in Montreal, we have very good connectivity, very high data rates, no problems. But when we go a little bit up north, the communities become satellite dependent. And in this map, you can see these ground station icons that are basically connected to the internet only through satellites. So if we can imagine a whole backbone is connected to this satellite. So when we talk about say few megabit per second data rates, clearly that cannot be sufficient to be able to connect the whole community. So satellites, especially high data rate satellites, are very critical to provide sufficient data rates and finally, so that we can achieve access equality in a global fashion. So they are rather essential and very promising. It can help us make sure that no one is left behind. Every community can be connected to the internet, which is basically considered a human right. So it is very promising. So as you can see, it's I started with a very positive tone on the developments on the satellite front. But being a researcher, we need to also consider the potential. We need to consider the potential benefits and the potential threats that are associated with this. So for that, I also have a couple of things to say before delving into standardization. So satellites are coming with very interesting promise of clearly connecting the backhauls, but not only connecting backhauls, they also come with direct-to-cell connectivity. They are promising us to connect our regular um, user equipments regular smartphones, laptops, to satellites directly by balancing the path loss. How can these path loss, how can we balance this path loss? One way of balancing the path loss is to improve the antenna gains. So how can an antenna gain be improved? By by making the antennas much larger. So one of these examples is basically ASC Space Mobile's Blue Walker constellation, which can enable us to connect to satellites directly with our unaltered cell phones. And the satellites actually have an approximately 700 square foot antenna array. So it is very good for us not to be able to, we don't need to actually change the equipment on our end. But what is different in this aspect is now when we are looking at these large antenna arrays, they actually harm other aspects. What are those things? First of all, we are creating a lot of light pollution that is impacting astronomers, and also we are creating interference, including RF interference, that is significantly, say, polluting the measurements by radio astronomy. So when we are actually sending these satellites up to space, we need to be very cautious about the interference that we are causing to the systems, including the light reflections. As you can see from the news bulletin on the right side, Blue Walker 3 is one of the brightest objects in the sky, and Starlink satellite trains are visible every night, and they are also affecting the radio astronomy. So this is one aspect that we need to be very cautious about when we are designing these networks. And another aspect that needs to be always taken into account, because we are increasing the number of objects in space continuously, that is basically generating a lot of traffic around the orbit. So this traffic and also potential collisions are very risky of creating an exponential amount of space debris, and the number of rendezvous and proximity operations when these objects get very close together is increasing significantly. So we need to be very cautious about the traffic management. So that's why I think this invitation from by Kamesh for the advanced air mobility is very important for me. So we need to be able to make sure that the space traffic management is also taken very seriously by all the disciplines that are that this is related to. So these are to be fair, we need to consider the advantages and the disadvantages, but now I will go back to the advantages part, and I will try to explain why this time satellite networks are different. First of all, clearly we have much improved processing capabilities, but in addition to that, one very promising let's say feature of these new networks is the standardization. The standardization is coming basically from different aspects, which we'll get to. But it is a must to be able to, let's say, manage these sophisticated networks. So this picture is a very oversimplified caricature of the 6G vertical networks. It's composed of a terrestrial network that is very dense in urban areas, and then also that should cover rural areas. We have a satellite network that is basically as the emerging components from these mega-constellations. And in between the two, there will be an aerial network which I see as a helper network. So I almost see this aerial network as the cream between the two Oreo cookies, and that can help us glue the top and the bottom, because otherwise there are so many other functionalities that we need to piggyback on communication aspects. So this aerial network can help us with a lot of these functionalities. When I'm talking about an aerial network, of course, drones can help us with those, or low altitude platforms. But one of the strengths that can help us glue with the satellite network with the terrestrial network is the stratospheric network. We are talking about high altitude platform stations that can be located at altitudes from 17 kilometers up to 50 kilometers. And this can be a significant feature, so that we can control the emerging satellite networks. So legacy control systems, legacy TTNs, telemetry, telecommand and control architecture may not be sufficient when we are talking about dense deployments of these satellite networks. So to define these networks, we are using the term non-terrestrial network. So there will be terrestrial component and the non-terrestrial component. And the non-terrestrial component is clearly will be composed of these satellite networks, which are emerging. But I also need to mention that there is a lot of standardization related fragmentation in the current constellations. Most constellations work in proprietary standards, including the Starlink constellation. However, it is clear that interconnectivity between them can be achieved. So when we are talking about this space network, it provides a favorable link budget when we are comparing with respect to former geosynchronous orbits, but it comes with its challenges, including very high mobility. I should mention that a satellite moves with a speed around 28,000 kilometers per hour. So we need to change connectivity between satellites approximately maybe 3 to 8 minutes period. So we need to make sure that this is all very let's say effectively coordinated. There is still latency when we compare them to terrestrial networks as well, and they are prone to some security concerns. And especially on the literature end, we also have an aerial network that's complementary to the non-terrestrial networks. There are some deployments and trials, for example, by Airbus. So this is the satellite networks will be complemented with an aerial network layer. The aerial network layer is I am seeing high altitude platform stations like a very important say tool that can complement the space networks. They are a bit more cost effective, although not frequently deployed. They have some additional advantages, but they also come with their own challenges if we are depending on the altitude. So how can we combine these networks and make sure that they work effectively, and then we can also come up with cost-effective consumer products? So the key word is standardization, and the standardization is getting along from the very many aspects. These aspects include the for example, the CCSDS perspective, which is managing the space missions. There is the DVB-SX perspective that is that has been working on satellite networks, mostly emerging from broadcast and multicast applications. And there's also very important branch of standardization that is emerging from the 3GPP standardization perspective. even starting from release 16, we can start seeing these satellite networks and stratospheric networks as a part of the standardization aspects. So this is a table that is showing that non-terrestrial network support has been around since release 15. So it's not we are not talking about a distant future to be able to standardize these networks. So of course, this is very promising from the coverage areas perspective. We are talking about hundreds of kilometers of footprints. What is critical that I will try to talk about it later on as well. What is critical is basically trying to coordinate the interference between these components, because now we are talking about overlapping footprints when even from a single network perspective. But there is also these constellations are also have some overlapping areas that and the overall interference needs to be taken into account. But if we are just focusing in a single satellite network, it is very promising because eventually it will we will see the evolution towards multi-connectivity, where we have a single terminal that is connected to two base stations, and these base stations will be located within the satellites. So here we can see the evolution. Also, we can see the functionality improvement in the satellite. The classical band pipe or the transparent mode satellites will no longer be around, and we are almost always talking about regenerative satellites that are capable of doing decode and forward transmission, and they can do also some additional computational capabilities. So where we are trying to get at is basically no talk is complete these days without talking about AI. We need to make sure that it is evolving in an autonomous manner. So this is basically the picture. The complex. This picture captures the complexity of the resource management that we can get towards. Now I will try to focus on some of the enablers of these connectivities. How can we achieve those? There are two problems. There are two fundamental problems that we need to tackle. One of them is to improve the connectivity between these nodes, and the second one is regarding the networking perspective. The first one is the connectivity. How can we enable connectivity? The two options that we have is basically RF versus free space optical. RF has its own advantages. It is it's a proven technology. We have high throughput satellites that can divide the beam into mini cells. Of course, this is very advantageous because of the relatively favorable characteristics in let's say like foggy weather, but it comes with its own challenges, especially from the interference management perspective. The second option is making use of lasers with free space optical. They can achieve extremely high data rates with very high bandwidths. They have lower power requirements. However, they are affected from atmospheric turbulence and very much from the weather impact, like fog, clouds, snow, and dust. And if you remember the picture that I showed, like regarding the northern territories in Canada, when we are satellite reliant, the weather may not be always favorable. So how can we, let's say, make the best of it? Most of the solutions that I have been focusing on in my research target some sort of a diversity. This diversity is either the use of RF and FSO in a hybrid manner or a mixed manner, or it can be a diversity in terms of not increasing the number of nodes or increasing the antenna arrays, and potentially making use of reflective intelligent surfaces. So as one of the first and promising solutions, we can clearly make use of RF and FSO in a joint manner, and we can simply select the favorable, say, connectivity depending on the weather conditions. So this is basically comes with a context awareness of the satellite. Satellite can have some information about the weather, and they can the network elements can switch between the communication links accordingly. So these are some performance curves that are showing the benefits of this. In the same setup, one other aspect that we can make use of is basically high altitude ground stations. So we can make use of a multi-hop setup. So from the satellite, we can go to a single or multiple high stratospheric platform, and this can help us bypass some of the issues. For example, satellite can always, there is no atmosphere, and there is very limited, I mean, depending on the altitude of high altitude platform station, there is limited, say, atmospheric events above the this platform. So the conditions between a stratospheric platform and station and satellite are ideal. So we can basically piggyback some of the mobility problems, which I'll try to get to later on, towards this stratospheric platform, and can help us obtain continuous connectivity. So other options that we can make use of these terminals, I am trying to be vigilant of the time in the meantime, is we can make use of these high altitude platform stations to be able to coordinate the activities, and can use satellites or stratospheric platforms to be able to connect two centers together. And in terms of the severe weather events, we can make use of multiple stratospheric platforms, and this can clearly improve diversity order and can significantly reduce the outage probabilities. So these are all options that can be used when we have connection, intermittent connectivity. And using multiple input, multiple output antenna arrays is always, of course, advantageous. Classically, satellites, of course, they have there are phased arrays, and this is a well-established technology in satellites. But we can also make use of massive MIMO kind of architectures if we can make sure that multiple satellites can be coordinated. So these advantages, we have looked into the advantages that can be provided with such a setup, and clear data rate benefits are seen in ideal conditions. Of course, there are still practical deployment problems that are including the potential duplexing, pilot assignment, feedback error, and the delay between the satellites, the changing delay between the satellites. As other features, we can make use of the reflective intelligent surfaces that can help the satellites to direct the beam, and this can be of special importance for reaching the rugged terrains that we still need to deploy IoT networks. So these are all solutions that can improve the connectivity. Now, my main focus here was to look at satellite to ground connectivity, but how can we improve the satellite to satellite connectivity? For that, one solution that is also promising is to bounce some of the signals from the stratospheric platforms that can help with the mobility, especially considering that a high altitude platform station is moving at a much slower rate. This can help us coordinate the mobility accurately. For satellite to satellite connections, lasers are the practical industrial solutions these days, but we can also make use of very high frequency bands like sub-terahertz and terahertz with very high directional antennas. Here we can try to benefit from the predictability of the orbital dynamics and capture the distances between satellites. So sub-terahertz and terahertz bands seem like a good solution to provide some sort of a diversity between inter-satellite links. Another say solution or feature that currently we are working on is integrated sensing and communications between these satellites. Here I have a picture from our former work with my student Gizem Sümen. With Gizem, we have actually tried to understand if we can make use of these high frequency bands to be able to accurately detect the reflections, which seems promising. Actually, currently we are working on a project supported by a Canadian Space Agency to see if we can use this dual functionality, and we are trying to design metasurface arrays to be able to have let's say space grade components that can actually work as high accuracy radars. So it is actually looking promising from these perspectives. Are like additional piggybacking functionalities on the already existing reception capabilities in the satellites. And if we step forward, how can these be used? Basically, these satellites will be the stepping stones to space networks. We can actually make use of them to improve lunar connectivity and then beyond Martian connectivity. And the role of LEO constellations with satellites can be significant as we move our work towards these space aspects. So what is going on from the networking perspective? That's also critical. Internet Engineering Task Force has been working on this interplanetary network paradigm for a number of years, and the delay tolerant or disruption tolerant networking is the emerging solution these days. Although with the scalability perspective, there's a lot of work needs to be done for this. So basically, we are in our research, we are trying to look into contact plan based routing solutions by making use of the predictability of the orbital dynamics. We can try to find alternative routing node options to be able to make sure that the traffic flow is not blocked or congested. However, of course, the real-time decision making in satellite is still not that easy. Usually, it's assumed that these routing tables are generated on the ground station, so there is still a lot of work to be done in this regard. With our joint work with Professor Halim Yonlu Kameroğlu, we are actually and also led by Dr. Pablo Modeori. We are looking at a simulation platform that can realistically obtain the potential performances of these networks. This work is supported by the Optical Satellite Canada Consortium and also by MDA. So how can we make use of these networks or make them function effectively? We need rather good location management, and this location management is a relatively new paradigm, especially when we are looking at this evolution from the satellite networking perspective, terrestrial networking perspective, because you almost never you see a base station to change its location except for the mobile base stations that were placed in trucks. Now we are looking at the mobility on the ground level and also mobility on the satellite level. So we need to make sure that we seamless handovers can be achieved. And for those, we can simply make use of virtual anchors as a solution. But here, stratospheric platforms can be significantly beneficial, especially when we want to do some computation. The computational capabilities of stratospheric platforms will be higher than the satellites. And the main reason for this, maybe it's worth mentioning, in space we can only make use of space-grade components so that they are resilient. If we cannot use we cannot just use a regular FPGA. They need to be radiation hardened. So what are the future research directions? There is a research problem at every level, and I find this fascinating because it's really if you look at the link it's simply connectivity. The question between RF versus FSO band, lower bands versus higher frequency bands, this is still a question that we need to answer. So there's a lot of decision that still needs to be taken into account from that perspective. So RF is advantageous in some scenarios, FSOs are advantageous in some scenarios. And especially when we go beyond satellite networks, for example, when we are talking about lunar networks, then we are facing regolith and lunar dust as a challenge, for example, for FSO, because it can cover the optical receivers, and that can significantly reduce the performance. So we can imagine like a small windshield wiper kind of architecture. So even this simple problem needs to be looked at with a new direction. Regarding the standardization, there are so many perspectives that needs to be answered. The mobility management to start with, spectrum management, fault tolerance solutions, intelligent management and orchestration, software-defined networking, network function virtualization, and possibly slicing in these networks, and routing. These are all the objectives that needs to be still worked along during the next few years. So what are we looking at when we combine everything together? We are looking at a deep vertical network, and this is one of my favorite pictures. So we have these local IP islands that needs to be connected with the rest of the terrestrial, infrastructure, and we are actually looking at locally congested traffic. So these are actually some of these aspects have not been considered. So for example, just to clarify what I mean, when we are looking at network layer, almost all problems are because of the congestion, but we don't lose any packets because of the, let's say, solar flares or solar activity increase. Now when we are looking at this network, the backhaul is subject to all sorts of interference. So we need to have a different perspective to be able to address the problems. Another concern that is relatively, let's say, highly mentioned in the literature is the spectrum management. Because when we are looking at a single constellation, it can be done, let's say, it is done, it works fine. But when we are looking at overlapping constellations, then we will have spectrum management problems. Regulations is also another concern because each band needs to be regulated, and we are talking about, especially when we are when these satellites are crossing continental Europe, every few minutes the satellite is serving a different country. All the roaming argument, let's say, principles needs to be satisfied, and the regulations should be set properly. So overall, I think this is a very complicated architecture, and then our legacy layered design is no longer, say, applicable. So we need to rethink of the communication system design. There should be no more layers. We need to somehow look at the problems holistically and solve them. And also looking at the satellite side, there's also an evolution in that regard. So each of these satellites are highly functional, and the target of these satellites is to achieve 1 terabit per second data rate. And I mentioned, like, we cannot use regular high-end FPGAs because they need to be space grade, and this is the technology is approximately 10 years behind the space technology is 10 years behind the current terrestrial equivalent. So how can we make sure that these are scalable? One of these solutions is to make use of multiple processors in a network architecture. So we are looking at a network on chip kind of, say, solution on each satellite, so that we can obtain sufficiently high data rates. And another question or important aspect that I would like to highlight is about security of these elements. So how can we make sure that these networks are secure? First of all, we don't have wireless channels. It's open to interference, and we need to be cautious about the security of these networks, because at the end of the day, if you remember, I started with this discussion of the space debris. We need to make sure that we need to minimize the potential space debris. So we need to make sure that satellites are operated in a safe manner. So overall, the standardization activities from the security aspect is at the say very early stages. I'm chairing the link layer of this standard IEEE P3349 space system cyber security working group. And I wanted to mention this because if you want to contribute, you can contact me, Nicola, or Greg, and we'll be happy to have you on board. So with that, I would like to conclude. Overall, with this evolution, we believe that 6G will leave no one behind, but there are still some technological, technical problems that we need to solve. And we are talking about complex interactions between networks, and we are certainly looking at a network of networks, and we are talking about a network on a single satellite. So I find this is very exciting times for research in this field. I would like to thank all my collaborators, Professor Halim Yanık-Ömeroğlu, Olfa, Eylem, Pablo Kürşat, Muhammed Abdüsadak, and many others. And I would like to thank the supporting agencies for funding my research. And if you have any questions, I can take them now, or you can later send me an email. My email address is shown. Thank you.
Thank you, Professor Gunes Kurt, for a wonderful lecture. And I believe you consider the time into account and presented in a level that fits the time very well, and also gave the significant or important aspects of research, combining with your own work that is going on in your lab. Thank you very much. I will actually ask. I have two questions. In fact, there are if anybody wants to ask questions, they can write in the chat message. But I will ask the questions, and if some question comes up, and I will give priority to the people in the group, in the audience. One is given of course, the complexity of sending a satellite with a communication system. You mentioned about simulations in your own lab, but in general, are there any testing facilities or environments that you are using or are in progress in Canada and other places that you are aware of for testing, any new concepts, like for example, mobility management?
Thanks, Kamesh, for this very important question. From the simulation side, this is a joint work with Professor Halim Yanık-Ömeroğlu of Carleton University, and the simulator that we are contributing to is within the Optical Satellite Canada Consortium support. So this is your question is very critical, because what I see in terms of the current developments is like a very fragmented perspective. So satellite operators have their own tools, space agencies have their own tools, and there's the compatibility between them is not that clear. For example, there are space debris databases, there is the satellite perspective. It's not we don't have a good way of combining all this data. And another perspective that was also, I think, hidden in your question is the almost near time requirements of these things. Because if we are talking about a meteor coming in, it needs to be taken into account immediately. So it's a very complex environment. As far as I understand, even the connectivity between these satellite operators or say Mega-Constellation are not very clearly standardized. Also, that tells me that the simulations are very detailed, but they are all focusing on specific perspectives, and the big global picture that you mentioned doesn't exist at the moment, as far as I know.
Wonderful. In fact, very recently, I happened to be participating in a meeting to begin the effort. In fact, in the meeting, we only discussed about what are the requirements. So that kind of, shows that even though there are a lot of opportunities and a lot of applications, that the challenges still remain in terms of creating such a test bed, for example. And obviously, it makes sense to have an international collaboration because of the nature of the problem. The second question I have is, about 3 years ago, I was involved in some discussions related to having a 5G base station on a satellite. At that time, I was thinking probably it is a very challenging thing, but then I've seen some efforts from some companies to do that. I believe efforts are already there, but probably there is already such a 5G base station on a satellite. However, some of the questions that were raised by, for example, some defense agencies, so it's extremely challenging because we need to modify the hardware. Of course, it is not going to be easy. So given this challenge, how can we handle this? For example, if you want to keep a a cellular base station on satellite, how can we actually do it effectively and cost effectively actually?
That's a very good question as well. So AST Space Mobile is one of these companies, and there's a T-Mobile SpaceX collaboration on Starlink terminals. We have Apple collaborating with Globalstar that can say actually use satellites, but Apple so not all of them are with provide high data rates. The current data rates are about 2 to at the best 2 to 4 megabit per second. So regarding the cost effectiveness of this, it's a bit of shifting the cost from the user terminal side to the satellite. Actually, this is what I see as the trend in the industry, because if you want to get a say specialized terminal, you need to get about you need to pay about $500 approximately, and if you can use your cell phone directly, that will be more cost effective. So it's basically trying to shift the cost to the satellite end, and I believe we will be seeing very low Earth orbit constellations very shortly, which will balance the link budget by due to their lower altitude. So that may be the reason that they are seriously being considered to reduce the cost.
Wonderful.
But maybe Kamesh, just one other thing that I would like to add. Keeping the satellites at that orbit is not that easy. So basically, it's a question of shifting the cost from the satellite part to station keeping, perhaps. So it will always be balancing between other things.
Yeah, I think the as you mentioned, it is extremely challenging, and there are a lot of work to be done, and collaborative efforts, not only between the agencies within the country but across the world will be required. Actually, I think. Yeah. Wonderful. Thank you very much for the presentation, and for this will be recorded and posted on the IEEE Knowledge Portal, so that anybody can view this along with the other lectures, other past webinars. And thank you very much, and have a wonderful day. Thank you.
Thank you, Kamesh, for the invitation.